So unfortunately, linear 17-point algorithm that we've seen, it will not work for any configurations of the general camera. We'll look at the degenerate cases under three configurations, in particular, the locally central projection, axial cameras, and the locally central and axial camera configuration. Now we'll follow the notation of the paper that proposed this analysis of the degeneracy written by Hong Tong Lee that I have mentioned in the acknowledgement slide earlier on. So suppose that we have an image ray. So in this case, it will be the same general camera. Suppose that we have an image ray, which we call L, with a point that we conveniently chosen as the camera center. That this is mentioned earlier on in when we define the Plucker line or the Plucker light ray for that denotes a point in the general camera. So here we are going to denote this camera center as V or any point on the light ray as V. And this light ray would also have a unit direction which we denote as X. Hence we can denote the light ray as a sixth vector that we have seen earlier on as X transpose, the unit vector, and a moment vector of V, which is any point on the line cross the unit direction of the line. And using this representation, we can then restate the generalized epipolar geometry, which is what we have defined previously as this form over here in the coordinates of x and v that we have defined. So r and t here will be r and e over here, where e is equals to the cross product of t and r, where t and r are simply the relative transformation. These are the relative transformation between the two general views. So the generalized camera view here, I have a corresponding light ray, and which intersects at a 3D point, and here R and T simply represents the relative transformation between these two generalized frame. But now we are rewriting it in terms of X, the unit direction, and the center of the camera, which we denote as V over here. So our goal here is to examine the various structure, in particular the three different configuration of the general camera under which this set of equations would produce a different set of solutions. We'll identify the several degeneracy for the set of equations from this general epipolar geometry such that it has a rank that is smaller than what we expect. As we have seen earlier on, that this generalized epipolar geometry equation over here, given sufficiently enough points, we can rewrite this into the form of E equals to 0, where E here it's our 18 by 1 vector, and A here would be n by 18, that is made out of the known variables from the Plucker line coordinates. And the 18 by 1 vector of E over here would be the unknowns that is made out of the essential matrix. The first 9 by 1 entry would be from E, and the next 9 by 1 entry would be from R. So we saw that from the linear 17-point algorithm, we will make use of A E equals to 0, the homogeneous linear equation, to solve for the SVD of A such that the solution to this particular equation, E, will be the last row of this right singular vector that corresponds to the least singular value after taking SVD of A. So here we saw that it will end up with a one parameter family of solution, provided that since this is 18 by 1 vector, this means that for this homogeneous linear equation to have a one parameter family of solution, the rank of A must be equals to 17. So in the case where degeneracy occurs, we can say that the rank of A would drop below 17. This means that we will have a family of solution which can be parameterized by more than one particular parameter. We could have two parameters of solutions or more parameters of solutions depending on the severity of the degeneracy over here. So in general, we will say that if the rank of A fall below 17, then we would have a degenerate case. So assuming that there are at least R number of equations that arise from the point correspondences via the generalized epipolar geometry, we'll see that the number of solutions that arise from the equation of AE equals to 0 would be 18 minus R. That means that the system must a rank of no greater than R over here. For example, in this particular case where we have 17 point correspondences, suppose that these 17 points, where R equals to 17, they are all linearly independent. So what this means is that we'll have altogether 18 minus 17 equals to one parameter family of solution over here. And this is the case that we have seen earlier on. So in the case where the rank dropped below 17, this means that R here is going to be lesser than 17, which also means that out of these point correspondences, all the R number of point correspondences, they are not all linearly independent. So we'll have lesser than 17 linearly independent constraints over here. And as a result, we will get 18 minus R parameters of a solution where the rank is no greater than R. So in the most general case, the camera is simply a set of unconstrained images in general position. So in this case here, the rank is going to be 17, and from 17 point correspondences, a unique solution can be obtained via the linear 17-point algorithm from solving the SVD. And in this case here, what it means is that suppose that this is view 1 of the generalized camera, so V1, and this is view 2, V2 of the generalized camera, where the V1 and V2 are the reference frame of the generalized camera. So here, suppose that this generalized camera is made out of a multi-camera system where C1, C2, C3, C4, they are individual respective camera. So in the most general case, what it means here is that suppose that this C1 sees a particular 3D point in the space, and in the most general case, its correspondence, the point that is being seen in the next view, the same point here seen by C1 in the next view of the generalized camera, would not be from the same camera itself. It would not be from C1. This means that this particular 2D point or 3D point here is not tracked over the generalized camera in the same camera under the multi-camera setting. So in this particular case, this would be the most general scenario where the 17-point correspondences would be linearly independent, and there would be a unique solution as we have seen earlier on. In the case of locally central camera, we will still have the two-view general camera, but in this particular case, we can see that the same point is tracked by the same camera in the multi-camera system setup. Suppose that this is our generalized camera for view number 1, and this is the generalized camera for view number 2, where it consists of a multiple camera setting. Here altogether there are 6 cameras on the general camera. So suppose we can see an example here. Suppose that we have a camera C1 over here. It's looking at a 3D point. Suppose we call this X, and the same 3D point, it's being tracked by the same camera in the second view of the general camera here. We can see this happening for every other point. It's always tracked over the same camera. For example, this second point here is tracked by camera number 2 in the multi-camera system setup, and so on and so forth. So in this particular case over here, since the light rays are represented in the coordinate system attached to the camera rig, we can write the correspondence between the points as xi, vi. Its corresponding point would be x, there's a missing prime over here, xi prime and vi prime, where vi and vi prime are the camera center of the respective two views. So what this means is that I have the first view and the second view of the general camera. And here, in this general camera, it consists of multiple camera setup, where VI over here, it's the camera center of the first view, and VI prime over here would be the camera center of the exactly the same camera in the multi-camera setting, in the second view over here, and XI would be a point that is seen by this particular camera in the first view, and xi prime would be the corresponding point that is seen by the same camera in the second view. So these two light rays would intersect at a certain 3D point that gives rise to xi and xi prime, the correspondence. So substituting this pair of corresponding points and the camera centers into the general epipolar constraint that we have derived earlier on, we'll get this equation over here, where now the transformation of the second view can be written as camera center of the first view instead of having a vi prime in this case here. So now we will have vi, which is coherent since they are the same camera center with respect to the same reference frame. So this, after the rigid transformation, the reference frame of this generalized camera with respect to the camera that we are interested in would not change. Now, we can easily see that E and R, it's one solution out of the family of solutions that we can obtain here. This is because of the generalized epipolar constraint that we have seen earlier on, that E and R, plugging it into this equation here, would fulfill the constraint to be 0. And we can also easily see that 0 and identity, where the essential matrix equals to 0 and the rotation matrix now equals to identity. It's also a solution to the generalized epipolar constraint. This is because substituting this guy here, the essential matrix here to be 0 and the rotation matrix here to be identity, we can see that this guy here, it cancels out. And here, since R here becomes an identity, we can see that these terms here becomes the sum of a antisymmetry of the triple product, which is shown by this term over here. And this term here, in linear algebra, we know that this is always equals to 0. Hence, 0 and identity would fulfill the generalized essential constraint. And generically, the rank is now not lesser than 16. That means that a complete solution to this generalized epipolar constraint will therefore have a two-dimensional linear family of solution given by E and R, which is the general solution that we have seen earlier on. So this can be parameterized by one family of solution, and as well as the other solutions that we have seen, which is 0 and identity. So we can combine these two sets of equations to give us the two parameter family of solution, which is lambda E and lambda R plus mu and I. We can easily see that this family of solution over here fulfills the generalized epipolar constraint by plugging it into the generalized epipolar constraint that we have derived earlier on. We can see that this can be easily decomposed into the addition of two terms. The first term here, which we will see that it's exactly the original generalized epipolar geometry constraint, which is always equals to 0. And the second term here, which is parameterized by mu, the second parameter that we have defined earlier on for the solution, would also be always equals to 0, since this is a result of a triple product. Hence, the addition of these two terms will always be equals to 0. That means that this particular solution that we have defined here, it has to fulfill the generalized epipolar constraint. An interesting property of this set two-parameter family of solution is that the ambiguity is contained entirely in the rotation matrix, because we can see that the solution here, E essential matrix, it basically remains as the essential matrix, which is up to a certain scale, and but the rotation matrix here would become a two-parameter family of solution, lambda R plus mu multiplied by identity. And This means that the essential matrix, we can still determine it up to a scale, but the rotation matrix will not be able to identify it uniquely anymore. So it's also interesting to see under this particular configuration, the locally central projection camera, we can see that under pure translation, this means that if the rotation here becomes to identity, we can see that this whole term here would become a triple product, because this would be lambda multiplied by identity. We can split this up into two terms of identity, which means that we will get this twice. We'll get this whole term here multiplied by lambda plus this particular equation over here. In this case, this term here would become this term here, and we will get this particular term here to be equals to 0. So what it means here is that this triple product will vanish under pure translation. This means that t is not equals to 0, but r is equals to identity. And we can also see that under this circumstance that the generalized epipolar geometry, it actually degenerates to the epipolar geometry of the normal pinhole camera, because only this particular term here remains, since these two terms here they are all going to vanish because of the triple product symmetry, and hence in this case we can see this here. So in this particular case, under pure translation, we can conclude that it's never possible to recover the scale of the translation here, because it's equivalent to the single pinhole camera epipolar geometry. The second configuration that we are going to look at would be the axial camera configuration. So this particular general camera is defined as the case where all the light rays, they are all going to intersect in a single line. This means that there's a single line axis which defines the camera center of the multi-camera system setup. One example here would be, suppose that this is the rigid body or a rigid rig that contains the multi-camera system setup. All the individual cameras, they are all going to be mounted along a particular axis over here. This particular line over here is what we call the axis. And there are several examples where this could be of practical interest. The first would be the stereo setup that we have seen earlier on. So in this case, for it to be a general camera, this means that the pair of cameras, they would not have overlapping field of view. It could be placed very far away where the amount of overlap in the view would be minimal, or it could even be a pair of cameras setup where one is looking forward and one is looking backward. So in this case here, a practical setup can be found in actually your mobile phone, where you can see that generally your mobile phone has two cameras, one in front and one looking at the back. So because this two cameras, they are mounted so close to each other, that means that the thickness of your mobile phone is actually very small, and hence these two cameras here can be treated as an axial camera. Another case would be a set of central cameras with a collinear center, and this is what I have shown earlier on in this case here, where we can see that there's a set of central camera, a multi-camera system setup with a set of cameras that where all the centers of these cameras sits on a straight line on the axis, which we call the axis over here. So in this case, it would also be an axial camera, and in the third case, it would be a set of non-central Catadioptric cameras or fisheye cameras mounted with collinear axis. And the first two cases here, since they are also central camera with a single point of convergence for every particular camera in the multi-camera setup, this would be both a locally central and axial camera setup. Here's an example of a catadioptric camera where it can be realized using a central camera that is looking at a semi-sphere lens that looks something like this, or a mirror that looks something like this. So when we project when lights are being projected onto this camera, they are scattered in different ways, where we treat the mirror here as our lens. This light rays that are reflected from this particular lens, the semi-sphere lens over here, they do not converge at a single center of projection. And similarly, for fisheye camera, here's an example of fisheye camera that you can purchase to mount it onto your mobile phone, for example. So in this case here, since there's a wide angle field of view, well, we can also treat these light rays not to be converging at a single center of projection. I will not go too much into the detail of the two models, or the camera models of the Catadioptrics and the fisheye cameras, but here these two cameras can also be generally treated as a non-central camera. So now let's assume that the origin of the world coordinates of these two general cameras lies on the axis. So what it means is that suppose that I have this general camera where there is an axis and all the cameras are going to lie here, and this is the same but of the second view. So here I'm going to define the reference frame of this particular general camera on the axis itself. Hence we may write the center of the cameras, which we denote as Vi, to be equals to alpha I multiplied by W, where W is actually the unit vector or along this particular axis with respect to the origin or reference frame. And similarly for Vi prime in the second view. Here, these two are the same camera except for they are in two different views. And what this means is that this particular guy over here, the axis, is still going to be along the direction of W, except for now there's a different scale of alpha I prime and in the direction of the axis. And by plugging in these two V values, the camera center values, into the generalized epipolar constraint, we'll get this particular equation over here instead of being expressed with respect to Vi and Vi prime. Now we express it in terms of alpha I and alpha I prime and W over here. So generically, we can see that this has a rank of 16. The reason is because here, in this case here, we can work it out where the E and R would generally still be a solution of this generalized epipolar constraint, but we will have an additional solution over here, which is W and W transpose for R and 0 for E. Hence, by combining, we'll do the same thing. We combine these two sets of equations together. We'll get this family of two parameters solution for this particular equation over here. And I won't go on to prove it here, but you can verify this by plugging in this equation back into this generalized epipolar constraint equation over here, and you will see that you'll still end up with a set of equation that is equivalent to the original generalized epipolar constraint, and the other set of the equations, which is addition, to be consisting of the triple product, which is always going to be 0. Hence, the solution here, the family of two parameter solution here, is always going to fulfill the generalized epipolar constraints to be equals to 0. Now, what's interesting here is that we can also see that in this particular case, the ambiguity only lies in the R part of the solution, which can be seen here. So E here can still be determined up to a certain scale, but R here, we will have a family of two parameter solution where there's an additional component over here. So in contrast, or compare this with the previous case of the central projection camera, where we have the solution to be delta lambda E and mu or lambda R plus mu of I. So the ambiguity also lies in the rotation matrix. Similarly, in this particular case, we can see that the ambiguity also lies in the rotation matrix. And it is important to note that the fact that this happens, or this particular ambiguity, only lies in the rotation matrix but not the essential matrix. The reason is because we choose the coordinate system to be on the axis itself. So here it means that we chose this particular reference frame to be on the axis. Hence, we can derive this particular form of solution where the ambiguity only lies in the rotation component of the solution instead of the essential matrix. It's important to also note that in general, if we were to choose axis or a reference frame that is anywhere uh, not on the axis of the cameras, then this ambiguity cannot be so well defined. This means that the ambiguity generally spills over to the essential matrix as well. But the rank deficiency will still uh, occur. So we have also seen in the earlier case that of a locally central camera that there's a degeneracy, and we also seen that for axial cameras there are two cases where it can also be defined as both axial camera as well as a locally central camera. That's the case where we have either a pair of camera that lies on a axis. It could be non overlapping field or view camera, or it could be an array of cameras that lies on the same axis. So these are cameras with central projection or locally central camera that lies on an axial camera configuration. Hence, it has both the property. And we'll see now that in this particular configuration, further degeneracy occurs. So the condition of the local centrality means that alpha I equals to alpha I prime. That means that the scale of both the frames having these two general camera frame, uh, defining a reference frame over here. Suppose that this is the camera I and this is camera I. We can see that even though the view changes, alpha I over here and alpha I prime over here, that used to define the position of the camera with respect to the reference frame will not change, because essentially these two are the same camera. So we are not moving this particular camera, it's rigidly fixed onto the axis. And by plugging this relation alpha I equals to alpha I prime back into the generalized epipolar constraint, we'll get this particular equation over here. So from the new generalized epipolar constraint that we have obtained from the locally central and axial cameras, we can further identify a solution which is zero and the skew symmetric matrix formed by W, which is the directional vector of the axis in a generalized camera that we have defined earlier on. So we can see that by plugging this back into the generalized epipolar geometry, we'll end up with this particular equation over here, which is always zero. The reason why this is always zero is that because we can see that this here and here, they are the same. But in this particular case here, we are taking W cross with I. This means that it's going in this direction, for example, and now we are swapping the position of X and W and do the cross product again. This means that we will get a vector that is equal and opposite in the direction of this vector over here. And adding both up, this means that they will become zero over here, which means that this guy over here is one of the solution that we will get from the locally central and axial camera configuration, and putting everything back into the previous solutions that we have from the locally central projection camera as well as the axial camera, we'll get a whole family of solutions which consists of four parameters over here: alpha, beta, gamma, and delta over here. So in this case, we can see that E and R, it's from the original epipolar constraint, and then we will get zero and identity, which is from the locally central configuration. And then we will see that there is also the omega from this particular locally central and axial configuration. And finally, W multiplied by W transpose, it's from the axial camera setup. So similar to the axial camera configuration, the complete solution set is under the assumption that the origin lies on the camera axis. So in this particular case, we have a general camera and there's also an axis. So every one of this multi-camera system that is fixed onto this general camera lies on the camera axis. And now we make the assumption that the camera reference frame has to be lying on this particular axis in order for the ambiguity to lie only on the rotation part. So in general, if we were to fix this particular axis anywhere on the rigid body over here or anywhere in the 3D space, then the ambiguity can get spilled over to the essential matrix, and this would be much more difficult to handle, as we will see later in our lecture. So once more, the E part over here can be determined uniquely up to scale, and there's a four-dimensional family of solutions here. We'll see later that we would not need to decompose E into four different solutions. In fact, we'll only take the two rotation matrices that we can decompose from the essential matrix to get the solution. So having defined the three different configurations of the degeneracies for our generalized camera, we'll now look at how to solve the equations under these degeneracies. We'll see that this will still remain as a linear algorithm, which will allow us to solve for the solution uniquely instead of having a family of solutions that is parameterized by two or more parameters that we have seen earlier on. So we know that for each point correspondence under the generalized epipolar constraint, this is the constraint that we will get from one particular point correspondence. And we have also seen that if we are given many point correspondences, we can stack these equations up into the homogeneous linear equation of this form, where A here is generally n by 18, and the vector is a 18 by 1 vector, where the first 9 by 1 entries would be formed by the unknowns from the essential matrix. The last 9 by 1 vector over here would be made out of the 3 by 3 entries in the rotation matrix. And however, we also see that typically under the degenerate cases, if we were to apply the standard SVD to this particular homogeneous linear equation over here, we'll get a family of solutions which is more than one parameter if the rank falls below 17. So in this case, because we saw that the solution would correspond to the SVD of A, in this case it would be, let's denote this as U, sigma, and V transpose, and the solution would correspond to the last row of this V matrix that corresponds to the least singular value in the case where the rank of A equals to 17. But in the case where the rank of A falls below 17, this means that we would be under one of the degenerate cases, as we have seen earlier on, where the rank could be 16 or lesser. For example, if the rank of A equals to 16, then what it means is that we would have to take the last two columns of V here to be the solution. And the solution of this vector over here, the 18 by 1 vector over here, would be parameterized by V1 plus gamma V2, for example. So where V1 and V2 corresponds to the last two columns of the right orthogonal matrix of the from the SVD of the matrix A. So this means that we would have a whole family of solutions if we completely ignore the rank deficiency here. Or worst case is that if we completely ignore the rank deficiency, that means that we don't care about the rank efficiency, the SVD of A still exists. This means that this guy over here, the factorization into this form over here, it still exists, but we might be taking the wrong solution, assuming that we thought that this A has a rank of 17, which in fact that it is lesser than a rank of 17. So we might mistook the solution to be just the last column of V over here, and that would be a totally wrong solution. Hence, we will now show the derivation of a solution that completely avoid degeneracy or this ignorance from happening. And the observation here would be that the E part of the solution is always unchanged by the ambiguity. And this is what we have observed in the solutions under the three degenerate cases that we have defined earlier on. And we'll make use of this particular property that the E part remains unchanged to derive the linear algorithm under the degeneracy. And thus, we'll rewrite this equation over here, which is the homogeneous linear equation that we've seen many times in this lecture now. So this is the general essential constraint that we have seen many times, and what we aim to achieve by finding the solution would be that we want to minimize this generalized epipolar constraint such that it's subjected to the norm of the essential matrix to be equals to 1. Hence, we are ignoring the norm of the whole vector over here, which we have been doing for the generalized linear 17-point algorithm. So in that particular case, let's write this as the vector as x. So we are solving ax equals to 0 subjected to the norm of x to be equals to 1. If we simply take the SVD of A and solve for the solution from the SVD of A, so this means that we are doing this, but now we are not going to do this anymore because we noted that under the degeneracy, the only thing that remains consistent would be the solutions for the essential matrix, and hence we can ignore the part from the constraint from the rotation matrix and simply solve this particular equation, this minimization equation over here, with respect to the or subjected to the fact that the norm of the essential matrix must be 1. So we can rewrite the generalized epipolar constraints into this particular form over here, where we can see earlier on that we have this constraint, the generalized epipolar constraint A multiplied by a vector of E, which consists of the first 9 by 1 entries of the 18 by 1 vector, and the second part of this vector would be R equals to 0. So we can split A into two parts. This means that I can write A as AE and AR over here, where AE is the first m by 9 entries of A, and AR would be the next m by 9 entries of A, and this can be multiplied by the same vector of E and the vector of R over here. So we can rewrite this into a summation of AE multiplied by the vector of E over here and AR multiplied by the vector of R over here. This would still be equals to 0. And now we can rearrange this equation over here. So we can rewrite this equation over here into AE, the vector of E transpose equals to minus AR V, the vector of R transpose, simply by moving this guy over here onto the right side of the equation. So we can now solve for the vector of R by simply taking the pseudo inverse of AR, and that would be equals to AR pseudo inverse denoted by a superscript of plus over here multiplied by AE and the vector of E transpose over here. So plugging this guy back into this equation over here, vector of R over here, we can eliminate this vector of R from this particular equation and rewrite it into the form of AE vector of E transpose plus AR multiplied by this equation over here, which is minus AR plus AE and the vector of E transpose equals to 0. So we can factorize out AE multiplied by the vector of E, which is here, and then the other parts here would be simply equals to AR multiplied by AR transpose minus away identity in this case over here. So we can rewrite the equation into this form, which as a result still ends up to be a homogeneous linear equation, because we can see that this component over here, which is made out of AR and AR plus and AE, they are actually a known matrix over here, which now simply becomes a n by 9 equation over here, where the vector of E would be a 9 by 1 vector that consists of the 3 by 3 entries in our essential matrix. And since this n by 9 vector here is a known vector, and this would mean that this whole equation over here would still be a homogeneous linear equation that we can easily solve by taking the SVD of this whole block of m by 9 entries of the matrix over here. So the last vector, the last column of the V vector that corresponds to the least singular value would be the solution for this homogeneous linear equation, subjected to the fact that the norm of the vector of E would be now equals to 1. Hence, we will be able to solve this without any ambiguity on the essential matrix. So, as I mentioned earlier, that the solving this particular equation with the standard SVD method would give us a unique solution for the essential matrix. We can then decompose the essential matrix according to the method that we have seen in the epipolar geometry lecture, to get the pair of rotation matrices, which we denote as R and R prime. So now, instead of further using this R and R prime and the essential matrix to get the other pair of the translation vector, we are going to make use of the generalized epipolar geometry that we have seen earlier on here to solve for the translation vector. We'll do this by plugging this R rotation matrix into this generalized epipolar constraint individually. So for each R, we'll do this individually, and then we'll solve for the translation vector here. So note that after we have plugged in R into this generalized epipolar constraint, this equation over here would be linear with respect to the translation vector, and we can form this into an equation of A t equals to 0, where t over here would be a vector of tx, ty, tz, and 1 transpose. And then we can solve for this t over here without any ambiguity by enforcing the constraint that the last element would be 0. So this can be simply solved as the SVD of A, and this would be equals to U sigma V transpose. We take the last column of V that corresponds to the smallest value of the least singular value entries in sigma over here. And since we have a one family of solution, which means that we have the lambda of V I, the last column of this particular matrix over here, we'll be able to solve for lambda, the parameter, by simply enforcing the last element of this t over here should be equals to 1. Hence, as a result, we'll get a unique solution for both R and T, since T here is solved by using this equation over here, where we have mentioned earlier on that X, which is X and X prime over here, since they are from the Plucker line light ray that is expressed in terms of the translation from the in extrinsic value with absolute matrix scale. This also means that the t vector that is being solved from this particular equation over here would also contains an absolute matrix scale. Compare this to the decomposition of the translation vector with the essential matrix. In this particular case, we will not be able to recover the absolute scale. So once we have the solution, because we have R and R prime from the decomposition of our essential matrix, This means that we get two possible solutions, and for each one of these R and R prime, we will plug it into the generalized epipolar constraints to solve for T. This means that we have the set of a pair of solutions which is equivalent to R and T and R prime and T prime. We'll check for the solution such that the 3D points are lying in front of both cameras. So for example, R and T, if it gives us the configuration such that all the 3D points lie in front of the camera, then we will choose this as the correct solution. As I mentioned earlier on, that we do not take the translation vector from the decomposition of the essential matrix because of the unknown scale. And in the case of the generalized epipolar geometry, we'll be able to get the absolute scale because of the knowledge of the matrix scale in the intrinsic value of the translation.